In this lecture, we're going to do some examples of a tensor density, and we're going to start with the most basic one, the Levi-Civita symbol. And I'm going to put symbol in quotes. I guess I shouldn't put it in quotes, because quotes kind of means in name only, right? So I want to sort of emphasize it. So I'll put like an asterisk on the front and behind. And the reason is I want to distinguish it from the Levi-Civita tensor, which is a different object. The Levi-Civita tensor is not a tensor density, it's a tensor. The Levi-Civita symbol, we will see, is a tensor density, and we're going to get and unpack that right now. So the way I want to understand that is we want to start with a no-kidding tensor. Let's start with a tensor. And that tensor is going to be well, let's set up our vector space, right? Our underlying vector space V, dimensionality capital N, and it's a real vector space R, and it will have a basis. Let's do a coordinate basis, partial sub I. So I is going to run from 0 to n minus 1, or from 1 to n. When we speak mathematically, it's always probably best to use I is from the set from 1 to n, because that just keeps it clean. But when we speak in terms of physics, we always try to go from 0 to n minus 1, because we like to distinguish 0 as the time coordinate, right? And we say, it's a little different. 0 is a little different. And it's because the metric handles the first coordinate differently. So we tend to go from 0 to n minus 1 in physics. Of course, in physics, we also choose n equals 4, right? For the certainly for the for the elementary version of advanced physics, we choose n equals 4. For the advanced version in advanced physics, you start having weird number of dimensions, and you can even speculate on multiple different versions of the time dimension, right? But anyway, I digress. The point being that we're going to have I go from 1 to n in our understanding. We're in the coordinate basis, and our underlying vector space is V. So now we're going to consider an element of the tensor product space, the tensor product space n0, right? So it'll be a n0 rank tensor of V. And the basis of this guy is going to be partial sub 1, dot, 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 oops. And I should start with the 1. Well, actually, no, that's not true. What am I doing? I'm getting confused with my partial sub j, dot, 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 partial sub I, and actually, it's been a while since I've done this, so I'm getting my own notation confused up. So it's I sub 1, I sub 2, dot, 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 all the way up to I sub capital N. That's the basis for this tensor product space. But of course, it's the basis. It's not equal to, it's a basis. So an arbitrary tensor in this basis will always have a component, I sub 1, dot, 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 I sub n, just like that. And again, the component is, we list the ordering of the component in the same order as the basis vectors, which is redundant, because this thing will always tell us what the relevant ordering is as far as the actual map that this whole tensor represents. But we do it redundantly because most of the time we don't carry this around, so the only way to preserve the identity of the particular tensor product space we're dealing with is to have the indices ordered in the component. Something I've been saying since the since the third or fourth lecture. So now, but we're now going to consider something specific, right? These components, by the way, can be any real number, right? There's no restriction on the real number. This is a vector space. That's a basis vector in the vector space, and the basis vector can be multiplied by any real number. So let's choose this. Let's take the Levi-Civita symbol, and let's make the Levi-Civita symbol the basis vector. I keep screwing that up. I1 let's make the Levi-Civita symbol equal to the components of this object. Now, that is a totally fine choice. It's a completely fine choice. And when I say it's a fine choice, what I mean is this resulting object is a tensor. It is a tensor. All right? There's no doubt about it. And the way we know it's a tensor is we know that it's the basis vectors of the tensor product space, and it's a real number times basis vectors. You add them up, the result, because of linearity, this object is a tensor, and there's no way around that. In the classical sense of things, what we're basically saying is that there's some tensor out there, E, and usually there'd be some bold face, E, and E equals in some coordinate system, E equals this guy, right? And it's as simple as that. Now, the point is that being a tensor means you transform like a tensor. And in the classical treatment of physics, you would tend to conflate, as I've always said, the components of a tensor with the tensor itself. Right? We're trying to get away from that by saying this is the tensor itself, these are the components. These are the components. And what we frequently would find ourselves doing is writing the tensor itself equals its components, where we use the same letter, I1 to IN, and we omit the basis vector, and we kind of conflate the components as being the tensor itself, and that's fine. Eventually we're going to do that, because we eventually, like I said in a previous lecture, we're going to take advantage of this classical view. Once we understand a tensor, then we can do the classical view with great confidence, right? But notice how in this case I basically said in this particular coordinate system, the components equal the Levi-Civita symbols, and now but there's also this tendency to name the components of a tensor E with the same letter and with the same letter, but just not boldface. But you give it you know its components because you have the indices there. So to blend these two together, what I'm basically saying is that the components of the tensor E in the one in the coordinate system, I guess I'll call this the unprimed system, meaning it's basically phi of x I sub 1. This is all shorthand, right? Everything is shorthand, and there's so much shorthand things get confusing. I sub n. This is literally what this means, right? This means that, right? So we have the unprimed coordinate system, and now I'm saying that the components of the tensor E in that unprimed coordinate system take on the values of the Levi-Civita symbol, right? And that is perfectly good. Okay, so now, what do we mean? Now we know that this thing, EI1 to IN sub I1 tensor product IN is a tensor. All right, we've agreed on that. So what does that mean? Well, that means that we can lower the indices of this guy. We can actually lower the indices. And what we're going to do is lower the indices with a linear transformation. So we know that the linear transformation lambda that's what we're going to call lambda the covariant transform, which means that lambda times the covariant basis vector, which would be a basis vector of V, would take that to the prime coordinate system, something like that. And therefore, lambda inverse would take the contravariant basis vector, or the basis vector of V star. This would be the basis vector of V. And lambda inverse would go the other way, like so. And so in this case, we're dealing with components that are contravariant and basis vectors that are covariant. So when we consider this, we consider the transformation of this whole tensor E, and we're going to substitute in the epsilon, or the Levi-Civita symbol for E, because we've decided that we're making that assignment. And I'm going to write the Levi-Civita symbol, I1 through IN. And let me erase this. And we're going to introduce the I1 through I prime 1, I1, dot, 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 lambda I n I prime n phi I n, right? And these are the transformations of the basis vector of the tensor. And then in order to keep this whole thing the same, of course, we use the inverse matrix over here, and we go I1 prime, and dot, 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 lambda I n prime. This is also the inverse matrix, like that. And that is the normal tensor transformation. This side here can immediately be replaced by psi 1 prime, dot, 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 I n prime, like that. And this now defines the new values of E I1 prime, dot, 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 I n prime. Now, you'll notice that these values here are not going to be equal to var epsilon I1 prime, dot, 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 I n prime. And the reason they're not is clearly because they're being multiplied by this matrices. These guys are plus minus 1 in this particular coordinate system. That's what the components are in this coordinate system. The unprimed coordinate system, the components of E in the unprimed coordinate system are these Levi-Civita values. But once you take it to a new coordinate system, the prime coordinate system, you're multiplying those pluses and minuses ones by these matrices, or by the various elements of these matrices, and you're doing a matrix multiplication. This transformation is arbitrary. There's like no chance that in the new coordinate system you're going to still have this var epsilon, or this epsilon, I should say, not epsilon, I should say this Levi-Civita relationship in the new coordinates. You just won't. But it's a completely legitimate transformation. You just have to accept the fact that in the only place where the components are actually equal to the Levi-Civita symbol is in this one particular system. And as soon as you transform, you start getting this mess, and you create new components that will not be equal to the Levi-Civita symbol in the other coordinate system. So that's why we can say that the Levi-Civita symbol is not a tensor, right? The Levi-Civita symbol does not transform invariantly in coordinate systems like that. Okay, now I previously posted this lesson, and I had, for some reason, I messed up and lost the first part of it. So what I'm now going to do is I'm now going to set this up exactly the way I had it, and then insert this in the front of the lesson. And so I started with that, of course, understanding that the dimension of the underlying vector space equaled n. And then we know that this also equals, this is now in the prime coordinate system. Oops. So I'm just sort of restating what I had written on the prior lesson, or the prior slide, and this is now the Levi-Civita symbol, because we're in one coordinate system where we've defined the value of the tensor through the Levi-Civita symbol. Now here I'm going to put in the prime. This is where we're left off, the prime. So this is already in the prime system, so that means each of these is already lambda I prime partial I, like that. Each one of these has already been replaced there. So we still have these guys over here, which make up E I 1 prime, E I n prime, like that. And of course, the old E I1 to In, that actually equaled the Levi-Civita symbol, and that's we set that up by definition, right? So we basically created this tensor by definition in one coordinate system so that the components had the Levi-Civita value, and then we noticed, well, when we do the transformation, we no longer maintain that value. And so with this, I'm now going to reconnect back with the last lecture and show you this interesting fact that we know about the Levi-Civita symbol that allows us to make progress and see the connection with the tensor density. Now, I'm going to do in red, there happens to be a relationship about the Levi-Civita symbols that we know because we've studied them so carefully. And it kind of goes like this. Let me see if I can write it down. Epsilon, I guess I'll have to say I1 prime through I, say, K prime. That, the Levi-Civita symbol in some prime system, it actually equals the Levi-Civita symbol in an unprimed system. And this is just a mathematical relationship, right? This doesn't have to do with systems of coordinates. This is just purely a mathematical relationship. If I have a Levi-Civita symbol using some prime indices and a Levi-Civita symbol using unprimed indices, if I take this unprimed guy and I transform each indices by some matrix A, so I guess it would have to be AI prime, like that, dot, dot, dot. I'm doing my A's backwards here, but it's all commutes, so it should be fine. Prime, like that. Right, these are just numbers, right? Matrix multiplication doesn't commute, but when you write it down in this component form where you're summing over indices, then each one of these, remember, is just a number, right? So those commute just fine. This process here will still convert all of these indices from prime to unprime, but this here is very similar to what we have here, right? And we know, but it turns out we know this other relationship, right? Where this will be, if I multiply by the determinant of A inverse, then I actually do have this really interesting relationship between the prime and the unprimed Levi-Civita symbol. Now, it is true that the Levi-Civita symbol in the prime coordinates actually equals the Levi-Civita symbol in the unprimed coordinates driven through the transformation by A, as long as, when I'm all done with it, I multiply by the determinant of A inverse, right? So this is an actual relationship. I may have covered this in my section on determinants. I probably should have if I didn't. But this is just a known fact about the Levi-Civita symbol. But it's very important because what it means is that I can, without much trouble, I can write this in the form that will be useful to us, meaning I can apply it to this. In other words, I take A to be lambda inverse and det A inverse to be lambda, and then I move this over to the other side, I guess, right? So what would it be? It would be well, okay, so det A, this would be det lambda, and these guys would be lambda inverse I k prime I k dot 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 lambda inverse I1 prime I1, Levi-Civita I1 dot 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 to IK, like that. And then I take this and I move it to the other side, and I get det lambda inverse epsilon, var epsilon I1 prime I prime K equals, right? And so this is this, right? And so I can make the substitution. I can make the substitution. And let's make that substitution. This is all pointless, so I can get rid of that. I can make that substitution, and I write it equals det lambda inverse I1 prime. Now I'm going to go to IN, right? Because here we are going up to n. Not so. This is, remember, this is just a general formula, right? From pure mathematics studies of the Levi-Civita symbol. So I make that substitution here for this, right? And then this guy here stays the same. I've already sort of substituted for it. And now I have E in the unprimed system, where it's very simple. It's just the Levi-Civita symbol as the coefficient for each of the tensor products basis, each of the tensor product space basis vectors. And now I have it in the prime system, right? This is the transformation to the prime system. Well, this was the transformation of the prime system, but then this nice little formula for Levi-Civita symbols allows me to write down this. And the point is that clearly in the prime system, the coefficients of this, the components of this tensor E is not just the Levi-Civita symbols. It's the Levi-Civita symbols multiplied by the determinant of the inverse of the transformation, the contravariant transformation. And this should not be a surprise, right? Because whenever you transform, that's the whole point of tensors, is you transform one coordinate system to another, the components change like crazy. And the basis vectors also change. And they change in exactly the right way to keep this object from acting rationally in all situations. And it requires that all, and what we'll learn in the general relativity course, is that all laws of nature have to be like that. You change the coordinate system, the ultimate object should not really change. And what that's saying is, you change the coordinate system, the basis vectors change in exactly the same way, in exactly the right way in relation to the components, that any formula that has the tensor in it is going to be ultimately unaffected. Everything's going to be invariant under coordinate transformations. So it's not a surprise that it would be really, really a shocker if you could transform this thing into any coordinate system and you would always end up with the Levi-Civita symbol in front, right? That would make no sense. There's no reason to think it would happen. But, it kind of comes close to happening, actually, right? All you end up with is this factor of the determinant of the transformation. So, but it's still not quite the same. What is interesting is that if we densitize this, just like we talked about in the last lecture, you can actually create an object that that does have the Levi-Civita symbols as coordinates in every single coordinate system. So let me do that. We'll create this thing called E grav, and it's going to look like in the unprimed system, like this, partial I1 tensor product, partial IN, like that. But then I'm going to do a tensor product with dx1 wedge to dxn, like that, right? Now look what we've got. This is going to be really cool because we know we've already worked on how this part's going to transform, right? We know it's going to come up with this, right? And we know how this transforms, right? Because we remember we remember from that when I'm going to transform these with the inverse matrix, so I'll do these, I'll just write it in sort of shorthand, wedge dot 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 wedge lambda inverse dxn. And we know that when we jam a matrix or a linear transformation inside a wedge product like this, or a maximal wedge product, right? It's going all the way to n. So we know that the dimension of V equals n. Oops, see, I wrote it down right there. I wrote it here again. The dimension equals n. So I know when I jam in any linear transformation inside a wedge product like this, the result is going to be, that's going to equal the determinant times dx1 wedge dxn, right? The determinant of that transformation. In this case, I'm using the contravariant coordinate change, so the determinant of the contravariant one comes out front. And of course, this thing is equal to dx1 prime wedge dxn prime. So if I want to now make the substitution of this, if I want to turn that into the primes, right, I have to multiply it by a factor of the determinant of the contravariant, transformation. But in order to keep everything equal to 1, that means I have to compensate for by adding a multiplication of the reciprocal of that, which is a determinant of the covariant, right? So now, now going back here, to transform this thing here completely, the first part, the substitution is right here, right? The second part, the substitution is, I'm getting a little jammed up here. The substitution for the second part is going to be the determinant of the covariant transformation, dx1 prime wedge dxn prime. This is what I have to substitute in here, right? Because the determinant of the covariant part times this, right, equals this. Oops, wait a minute. Equals this right here. So this thing here equals this thing here divided by this determinant, which is just multiplying it by the determinant of its opposite. Anyway, the point is that that determinant is going to cancel with this determinant, and you're going to be left with nothing but this as your components, right? Maybe I should actually do that out, right? Maybe I should write that out. So we're going to get, so I'm transforming this thing here, right? So I'll transform the first part. The first part is the determinant of lambda inverse times epsilon I1 prime dot 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 IN prime. And then the next part is I1 prime IN prime. And then the last part is got to be the determinant of the covariant matrix times dx1 prime wedge dxn prime. And this cancels with this, and you're left with just epsilon I1 prime IN prime di1 prime din prime times dx. God, I should do better with my d's. How would I? Maybe I should not worry about coming back down so hard. dx1 prime wedge dxn prime. And this thing here, right, actually looks identical to what we started with, which was this thing here, right? It's just now in the prime system. And by adding this term here, by adding, I'm going to go in blue now, by adding this guy, we've densitized this thing, but because of the nature of the Levi-Civita symbol, that densitization actually compensated, and we end up with an object that has a no-kidding Levi-Civita symbol as the component in every coordinate system. And this, by the way, I've never actually. This is sort of an exercise in the notion of densitization, but you won't see this discussed much in general relativity books. And this is not, by the way, the Levi-Civita tensor, right? This is just a densitized object that happens to have Levi-Civita coordinates or Levi-Civita components in every coordinate system. Okay, so that is the Levi-Civita tensor. That's what we're going to talk about now. I'll come back to it one more time after we talk about the next thing. And the next thing is the determinant. The determinant of the metric tensor. The determinant of the metric tensor. This is one you see a lot in general relativity books for a good reason. It's a very, very important idea. And without it, you can't really handle integration as it's handled in your typical general relativity context. There's actually quite a lot to the theory of integration on spacetimes and manifolds that have a lot to do with tensors and pseudotensors, and it's a subject that I really do hope to get into. It's actually quite advanced, and these lectures were never meant to be quite that advanced. But the determinant of the metric tensor densities is still, I think, it's probably in the advanced beginner or the intermediate level of general relativity. But it is an important subject, and we'll see that this is an example of a tensor density. First of all, the metric tensor, I'll just remind you, G, I guess if it was a boldface G, can be expressed usually, initially, when you just talk about it generically, you express it in terms of its covariant form. Like that. Now, there's certainly okay to talk about it in its contravariant form, right? Right, that is perfectly fine also. But we are going to talk about it in its covariant form. And it's a tensor. It's a tensor, and it's an element of the 0-2 tensor product space. It is a symmetric tensor. It's like the total opposite of a two form, right? It's completely symmetric in its indices. The thing about it is that it's special. This is the thing you always have to remember. It is special. And why is it special? It's special because it's traceable to a property of the underlying vector space V. You remember the underlying vector space V it was a real vector space. It has a basis, which I guess we're calling partial mu. It's got dimensionality of 4. But it also, if it's given an inner product on V, then that inner product, because V has the inner product, that inner product specifies a metric tensor. So the underlying vector space has the inner product, and this tensor follows from it. Now you can argue the other way. You can say, no, it's the other way. The space-time, especially if you consider this a tensor field, right? So there's a function, it's really a function of x. But the space-time has a metric tensor, and that drives an inner product into every space V. Either way, the point is the metric is special because it really communicates either from the underlying vector space to the whole space-time, or from the underlying vector spaces, because remember there's one of these vector spaces at every point in space-time, right? But it's a restatement, essentially, of a property of the underlying vector space, which was endowed, right? We had to give the underlying vector space this inner product. So we've already made an arbitrary decision, in a sense, an inner product on V, and that's given us this special metric tensor. And once we have that thing, we treat it like it's a very special 0-2 rank tensor. And therefore, talking about the determinant of of the metric tensor, it's not just like talking about the determinant of any 0-2 rank tensor, it's talking about a very special one, because we've made either this choice here or we've just chosen it explicitly. The idea, of course, in general relativity is that nature chooses this thing. Nature tells us what this special tensor is. And almost all of general relativity in one way or another has to do with trying to figure out what this guy is. Anyway, that's for another time. But so when I ask about the determinant of the metric tensor, everything I say is applicable in one way or another to any member of the 0-2 tensor product space. Any tensor A mu nu dx mu tensor product dx nu. Any such tensor, we can do the process we're about to do. It's just it wouldn't matter. It's only special for, it only really helps us for the special one, the special metric tensor. Okay, so how is this going to work? What are we doing here? Well, of course we're going to just transform the darn thing, right? We're going to say G mu nu dx mu tensor product dx nu. See if I can do my news better. Dx nu. We know that that's going to transform covariantly mu prime mu nu prime, and then I'll just, and then this will be G mu nu, and then I'll just go dx mu prime tensor product dx nu prime, right, where the contravariant transformations are buried in here, right? So everything's still multiplied by 1. And that equals G mu prime nu prime dx mu prime dx nu prime. And so now we just sort of, we can strip these guys off, and we'll just look at G mu prime nu prime equals these two covariant matrices G mu nu. I guess mu nu mu prime nu prime. So we just look at this, the straight up transformation of the covariant metric. So now we just take the determinant of everything, right? The determinant of both sides. So the determinant of G mu prime nu prime, it's the determinant of a tensor. I'll just write it down this way. And that's going to equal the determinant of lambda squared times G mu nu times the determinant of G mu nu. So this thing, just move it over here and write determinant like that. So what we see from this is that the determinant of the metric tensor, right, which, by the way, is defined as, let's see, how is it defined? It's defined as epsilon, say, alpha, beta, gamma, G, gamma, delta, G1 alpha, G2 beta, G3 gamma, G4 delta. This is just your typical definition of a determinant. Just because I'm only saying this because this is understood to be a matrix. So we know the determinant of a matrix is completely clear. And in fact, it's this, right? If G was a matrix, this would be the formula. It turns out the determinant of the tensor components is the same formula, right? It's the same formula. So the this determinant, when you switch from the unprimed to the prime system, right? It's got a factor of the determinant squared, right? It's it's got a factor of the determinant of the covariant transformation squared. So this thing here is transforming as a scalar density of weight 2, right? It's scalar because it doesn't have any tensor parts here, right? We're just looking at the determinant of this object. But it's still a transformation, and it's just a zero-order tensor, right? So it doesn't have these guys. But its transformation is still a scalar of weight 2. And the fact that it's a zero-order tensor, that's why we'll call it, instead of saying a tensor density of rank 0 of weight 2, or a 0, 0 tensor density, I guess we could say that. We could say a 0, 0 tensor density of rank 2, but we say it's just a scalar density of weight 2. And the reason it's a weight 2, of course, is because you got the square of this thing up here. So likewise, since it's a scalar, we can take square roots of both sides because it's just numbers, right? So, so it's conventional, by the way, just to use G prime and G. So this guy here is just called G, and this guy here is called G prime. And so we could write, so we write G prime equals det lambda squared G. And it's very common to write the square root of G prime equals det lambda times the square root of G. So the square root of the determinant is a scalar density of weight 1, right? So the square root of G, this guy, or I guess this guy, that transforms like a scalar density of weight 1 because there's no 2 here in the exponent, it's only a 1. So that's a scalar density of weight 1, this is a scalar density of weight 2. Likewise, I suppose G squared would be a scalar density of weight 4, right? So, so this is another example of this one's sort of an easy to derive little fact, but you have this G is a scalar density. The problem a little bit is with the square root. The determinant of an object can be positive or negative, and that's going to loom large if someday we talk about the orientation of manifolds and pseudotensors. But for now, excuse me, it is still true that the determinant of G can be it can be positive or negative, right? And it will so happen in general relativity, it'll very often be negative depending on how you choose the metric. So frequently they write it this way: the square root of minus G is the determinant of lambda times the square root of minus G prime. And you'll see that minus sign thrown in there because they know that the determinant of G is going to be negative. And they know that because the core matrix for G in flat space-time will be minus 1, 1, 1, 1. It's this pseudo-Riemannian matrix. Or the alternative is minus 1, minus 1, minus 1, 1, or the other way around. It doesn't matter. It's either got 3 negative signs or 1 negative sign, and regardless of whether it's 3 or 1, the determinant will be negative. So they put in this negative sign. Sometimes they don't put the negative sign, they just put in absolute values of G prime equals the determinant of lambda times the square root absolute value of G. So you'll see all 3 of those forms. But the point is that we have for free in any metric, any space-time with a metric, we have for free a scalar that is of weight 1 and weight 2, right? And so if we divide by 1 over, so 1 over G prime is going to be 1 over det lambda times 1 over square root of G. So there's also this formula. So we know that this guy here, the 1 over the square root of G, transforms like a scalar density of weight minus 1. And likewise, of course, 1 over g prime equals 1 over det lambda squared 1 over g, and that has a weight of minus 2. So we have a minus 1 object, a minus 2 object, a plus 1 object, and a plus 2 object, all based on this fact right here, this transformation right here. And it's scalar, right? So we don't have to carry around any kind of there's no tensor part to it, or it's just a number. And we're going to use that because I will use it in an example right now. We're going to show you how you can take what would have normally been a tensor density and turn it into a regular tensor just by using factor of the determinant of the metric. So how do we do that? Well, let's just go back to our Levi-Civita tensor. So this, we started with this object that looked like var epsilon. Let's do it down here. Let's go to the lower index now. I, k, like that. And, well, it's not k. Let's do n. And then dxi1 tensor product dxin, like this. And instead of looking at this thing as we've already kind of studied this thing to death, right? And we know that when it transforms, it's not going to transform into a system. It's not after transformation, it's not going to have Levi-Civita symbols as components anymore. But let's go ahead and make the transformation of this object. But we're going to include a factor of square root of the metric. And I'll use these little absolute value signs because they show up all the time. I mean, in all the textbooks they show that. So now we're going to study this guy, right? Before, we only studied this guy. Right, so now we're going to study the whole thing with this extra scalar term. Now notice, I'm not adding any pieces to the tensorial basis vector part. Like I did when I densitized this, I had to actually add another tensor piece, or an exterior power piece that's basically a tensor of sorts. This time I'm just multiplying by a doggone number, but that number is a function on the space-time, and it does transform in that special way that we've already described. So now how is this going to work? So I'm just going to execute the transformation using the normal methods. So that will mean that I have to multiply by the covariant matrix I1 prime, and I have to multiply by a bunch of them, in prime, and I1 to in, and then this is this dxi1 wedge dxin prime, right? Oops, why am I wedging? I'm not wedging. Sorry, this is tensor products, right? Tensor product dxin prime, like that. So that is this part here is just the regular transformation of this that you would have always seen. Now we have this factor here in front, right? That factor is the square root of g. So now this is what we would get if we just did the transformation. That we would just get these transformation matrices working on the components, and every component apparently has this factor of root g, so I've kind of lifted it out, so that's fine, you can do that. and these matrices are compensated for by the change from the unprimed to the prime basis. So buried in here are the inverse matrix, the contravariant matrices. So this is all still one. This is all still the same. But the next step is to say, well, I'm going to now multiply this. I'm going to multiply by the determinant of lambda times the determinant of lambda inverse, and I1 prime, in prime, epsilon I1 to in dx I1 prime dx in prime. So I've stuck in the number 1 in this form, right? And I'm going to lean back on my rule for the epsilon, or the Levi-Civita symbol, and I'm going to realize that this is just converts to a new Levi-Civita symbol of with the prime indices, and in this case they're going to be in the lower position, I1 prime, in prime. So this is the same rule here that we used. Let me see if I can find it still. That we used right here, right? That's this rule here, but it's, well, we applied it. We wrote it down this way, and we applied it backwards in the sense that we replaced A with the contravariant matrices. Now we're replacing A with the covariant matrices, so you'll get an inverse in the front, right? Which is what happens here. So these are the covariant matrices, and you get the inverse in the front. So this all works now with the covariant side of this this function, although I'm cautious to call it covariant. But you still end up with the no-kidding Levi-Civita symbol down there. And then this part here, right, well, that just becomes the square root of G prime. And so the whole thing is the square root of G prime of the times the prime coordinate Levi-Civita symbol times dx1 wedge dxn prime. So this is the full transformation. And you'll see it's got the exact same form as this does. So although we can never find a coordinate system where this object transforms in a way where you have a Levi-Civita symbol in every single frame, if you multiply it by this guy, this determinant of the metric tensor, because we know how that transforms, that transformation exactly compensates. So it turns out that this thing here is a no-kidding tensor. That thing is for real as a tensor. And you'll get an equivalent one with indices in the up position if you just work it out in the with sort of the contravariant form of the Levi-Civita tensor. So this is one of the ways that this thing is applied. You apply this to compensate for densities. This thing was a density, and it showed up by having this guy right here. So I just chose the right version of all this stuff, right? Of all this stuff, I just chose the right version. In this case, the right version was this one right here. And I threw it in the front of the density, and I de-densified it, right? And so now this guy really actually is a tensor. And this thing here is often called the Levi-Civita tensor, right? This thing is the Levi-Civita tensor sometimes. Don't get that confused in any way with the long, messy narrative I did about this thing, right? You might think, well, this is the true Levi-Civita tensor because this is the object that actually has Levi-Civita coefficients exactly as they are in every coordinate frame. Yeah, that's true, but This is some esoteric thing just to demonstrate a point about densitization. This is the guy that actually shows up from time to time in actual work on general relativity. Okay, so that's it for today. I just showed you a few examples. Let's see what we did. We covered tensor densities, the Levi-Civita symbol as a real tensor, as the components of the tensor. A Levi-Civita symbol doesn't cut it. It ends up being a tensor density, and remember, that analysis depended on knowing this fact about how the Levi-Civita symbol can be transformed from one set of indices to another using a linear transformation. And you need this determinant, which is what made it a density. But we did finally come up with this densitized thing, which did have those coordinates in every system. And then ultimately we found the determinant. The determinant of the metric tensor is a scalar density of weight 2. And the square root of the determinant is a scalar density of weight 1. And then you also have these scalar densities of weight -1 and -2, which are the reciprocals of these things. And we actually applied it back to the Levi-Civita tensor to show that this guy here actually is a tensor. All right, that's it for now. See you next time. I suppose for a moment I ought to remind everybody what the Levi-Civita symbol actually is. Notice I'm using this weird form of epsilon. It's actually called a variant epsilon. If you ever use a typesetting program, LaTeX, it's literally \var epsilon, as opposed to a symbol that looks like this, which is your regular Greek epsilon. They're different. We're going to use them differently, actually. So var epsilon is the Levi-Civita symbol, and it's defined as the Levi-Civita symbol of a permutation basically equals the sign of the permutation. So it equals +1 if the permutation is even, -1 if the permutation is odd, and 0 if sigma is not a permutation. Right, so a permutation will always be a sequence of numbers, in this case from 1 to n, representing the different coordinates. And if sigma will be some permutation of the numbers 1 to n. It might be, well, it would be sigma 1, sigma of 2, ... to sigma of n. And so if any of these values of sigma are the same, you'll have this not a permutation factor, and it's 0. And if this final permutation is an even permutation of the numbers 1 to n in order, then you get +1 for this Levi-Civita symbol and -1 in the other case. So that's the definition of the Levi-Civita symbol, just as a quick reminder. So now we have our components, ei1 to I sub n. Our components are going to be essentially +1 if I1, In is even. It's an even permutation of 1, 2 to n. -1 if this is an odd permutation of that, and 0 if it is not a permutation at all.